Up to this point, we have been learning on using the velocity triangle to analyze the flow behavior of a fluid when it enters the impeller and it leaves the impellers at the tips of the impeller. So in these ideal conditions, the fluid leaves the blades at an angle of beta prime 2, and this angle of the fluid leaves the impeller is identical with the blade angle at the outlet. So prime belongs to the fluids and beta 2 belongs to the blade angle at the outlet. In most cases, the conditions might not be ideal. Now we have two velocity triangles here, the red one and the black one. The red one represent the ideal conditions when we have these conditions, when beta prime 2 equal to beta 2, or the angle of the fluid leaves the impeller equal to the angle or the blade angle at the outlet. In actual cases, this might not happen, so the beta prime 2 will not be identical or equal to beta 2. So this is where the slip factor played roles. Due to the slip of the fluid at the impeller, we are having a smaller Cx2 at the outlet, or the tangential component of the absolute velocity at the outlet, or Cx2, becomes C prime x2. So due to the slip between fluids and the impeller, or the blade of impeller. So if we want to draw the angle here, so we have beta prime 2, and this is beta 2. So then again, remember that the red velocity triangle belongs to the ideal conditions and the black one belongs to the actual conditions. Slips normally occurs due to the pressure difference between the two faces of the blade. So we have a pressure gradient. So this is the low pressure region and this is the high pressure region. So this pressure difference between the two faces of the blade creates a non-uniform velocity distributions across the blades when the fluids pass the blade of the impeller. So one main source of the slip is due to the velocity, or due to the pressure difference between the impeller. Another thing that might cause this slip between fluids and the impeller, or between fluids and blade, is the distance between the blade of impeller that might cause the fluid unable to follow the curvature of the blade. So if we try to write it down, the first one is pressure difference between the two surfaces of the blade, and the second one is the distance between blades that creates, or that leads to the velocity unable to follow the curvature of the blade. So this slip leads to the delta Cx. Here we have delta Cx, which represents the amount of slip itself, Or on the other hand, we can write down this slip as a slip factor, or we can write it down in the Greek letter of tau as that equal to C prime x2 divided by C x2. So this is the ratio between this and this. There are three methods to estimate the slip factor of a centrifugal pump. These methods are based on the blade angle at the outlet, so it's based on the amount of the blade angle. So this three factor is known as the Stodola proposal. The second one is Gooseman proposal, and the last one is Stanitz proposal. The Stodola proposal can be used when the blade angle itself lies between 20 degrees to 30 degrees. So we can use the Stodola proposal that the equation itself is slip factor is equal to 1 minus P multiplied with sinus of blade angle at the outlet divided by Z multiply with 1 minus 2 the radial component of the absolute velocity at the outlet, or CR2, divided by U2 multiply by the cotangent of beta 2. That is the Stodola proposal when the blade angle at the outlet is equal to 20 degrees up to 30 degrees. So we have a new parameter here, that is Z, which is the number of blades. The second way to estimate the slip factor is by using the Gooseman slip factor equation. So in this case, when we have the blade angle between 30 degrees up to 80 degrees, we can use this Gooseman slip factor, which is a function of A minus B multiplied by the radial component of the absolute velocity at the outlet, or CR2, divided by U2 and multiply with cotangent of beta 2 and divided by 1 minus to the ratio between CR2 to U2 multiply with cotangent of beta 2. Here we have a new parameter also, which is A and B, where A and B are functions of beta 2, Z, the number of blades, and the ratio of radius of the impeller blades at the outlet and the inlet. So this is the source for us to define A and B. The third way to estimate the slip factor is by using the Stanitz slip factor. So these equations can be used, or best used, in the range of blade angle between 80 degrees up to 90 degrees. And the slip factor itself, based on Stanitz calculations, is equal to 1 minus to 0.63 multiplied by P and divided by Z multiply to 1 minus to the ratio of the radial component of the absolute velocity at the outlet divided by the blade velocity at the outlet and multiply with the cotangent of beta 2. So as the consequence of the slip factor, the Euler equations for the centrifugal pump that we know is E is equal to W divided by M, mass flow rate, and work divided by the mass flow rate that we knew it before as U2 multiplied with Cx2 minus 2U1 multiplied with Cx1. Due to the slips, we have to add the slip factor in front of the first part of the equations here. So we add the slip factor in front of U2 multiplied with Cx2. By doing so, we are counting the effect of slips between fluids and the impeller. So before using the slip factor equation, so be careful to have a look at the blade angle at the outlet, whether it is can be used for the Stanitz, Gooseman, or the Stodola slip factor.